What I'm about to tell you is something most scientists avoid saying out loud in public discussions. Not because it's wrong, not because it's fringe, and not because it belongs to science fiction, but because once you truly understand it, it changes the way you look at reality itself. And science, as it is usually practiced, prefers careful distance-measured language, controlled uncertainty, and emotionally neutral explanations. But today, that distance is gone. Here is the idea in its raw form. Most cosmologists now quietly accept something that is rarely stated so directly. We do not know what came before the Big Bang. We do not even know if before is a meaningful concept. And despite decades of progress, our best models of the universe still contain deep, unresolved anomalies, real, measured features of the cosmos that do not fully fit into our current understanding. Some of these anomalies are small on paper but enormous in implication. They suggest that something might have existed prior to the beginning of our observable universe. Something that left behind traces in the fabric of space itself, like a storm that ends but still leaves marks on the landscape long after it has passed. And the reason this unsettles scientists is not because it is irrational, but because the mathematics does not immediately reject it. The data does not fully rule it out. And if it is even partially true, it forces us to rethink what existence actually means. So let's begin at the beginning, or what we assume is the beginning. The Big Bang. The standard answer in cosmology has been simple for decades. Asking what came before the Big Bang is meaningless. Time itself, according to this view, started at that moment. Before requires time, and if time didn't exist yet, then the question collapses. It is often compared to asking what lies south of the South Pole. This explanation is elegant, it is clean, it avoids confusion, but it relies on one major assumption, that time truly began at the Big Bang. And that assumption comes from our current physical theories, especially general relativity applied to the early universe. When we push those equations all the way back, something strange happens. They stop working at the origin point. T equals 0. General relativity produces a singularity, infinite density, infinite temperature, infinite curvature. But in physics, infinity is not a physical answer. It is a warning sign. It means the theory has been pushed beyond its limits. It breaks down. It stops being reliable. So when we say time began at the Big Bang, what we are really doing is extending a broken equation into a region where it no longer applies. And that is not a conclusion, it is an extrapolation. When physicists try to go deeper using quantum theory, the picture begins to change. The singularity starts to disappear. Instead of an infinite point, the universe appears to reach an extremely dense but finite state. Something like the Planck density, an unimaginable concentration of energy, but not infinite. And in some models, this extreme state does not mark a beginning at all. Instead, it becomes a transition point. In these quantum descriptions, the universe may not have started from nothing. It may have emerged from a prior state or passed through a transformation that looks like a beginning from our perspective but is not the absolute origin of everything. And once that possibility appears, the question, what came before, comes back into focus, not as philosophy, but as physics. Because if the Big Bang is not the true beginning of time, then our universe may be part of something larger, something older, something that existed in a different form before everything we know came into existence. And that is where modern cosmology begins to split into multiple serious, competing ideas, each one attempting to describe what reality looked like before our universe took shape. And none of them are simple. One of the earliest attempts to answer this question is the idea that the universe is cyclical. Instead of a single beginning, there could be an endless sequence of expansions and contractions. A universe that grows, collapses, and then rebounds into another Big Bang, repeating this process without a final starting point. This concept was once called the oscillating universe. In its simplest form, it imagined a cosmos that expands after a Big Bang, slows down under gravity, collapses into a big crunch, and then bounces back into a new expansion. A never-ending cycle of cosmic birth and death. For a while, this idea seemed promising. It removed the need for a true beginning, but it ran into serious problems. Observations showed that the expansion of the universe is not slowing down, it is accelerating. That makes a future collapse unlikely. And thermodynamics introduced another challenge, entropy. Entropy measures disorder, and in every cycle, entropy should increase. If the universe had already cycled infinitely many times, it should now be maximally disordered. But what we observe is structure. Galaxies, stars, planets, and organized complexity. That contradicts the simplest version of the cyclic model. Still, the idea did not disappear, it evolved. A more advanced version came from modern theoretical physics, especially work involving string theory and extra dimensions. In this framework, our universe might not be alone. Instead, it could exist on a kind of membrane, called a brain, floating in a higher dimensional space alongside other brains. In this picture, the Big Bang is not a beginning but a collision. Our universe could have been created when two brains moved through higher dimensional space and collided. The impact released enormous energy, creating the hot, dense early universe we observe. After the collision, the brains separate, drift apart, and eventually are pulled back together by gravity operating through higher dimensions. Then they collide again. Another Big Bang, another cycle. This is not just abstract math. It leads to predictions that can be tested. One key prediction involves the cosmic microwave background, the faint afterglow of the early universe. In standard inflation theory, the early universe should produce certain gravitational wave patterns, which would leave a detectable signature in this background radiation. But in the cyclic brain model, those signals should be extremely weak or nearly absent. So far, experiments have not confirmed the expected strong signals from inflation. Instead, results have placed tighter and tighter limits, making simpler versions of inflation harder to maintain without adjustment. This does not prove the cyclic model is correct, but it keeps it alive as a serious possibility. It also highlights something important. Our understanding of the universe's beginning is still incomplete. And there are even stranger ideas. One of the most developed comes from the work of Roger Penrose. His proposal does not rely on collisions or bounces. Instead, it suggests that the end of one universe and the beginning of another are actually the same event, seen from different perspectives. Roger Penrose proposed a radically different idea, known as conformal cyclic cosmology. Instead of a universe that bounces or collides, he suggests a universe that transitions smoothly from its far future into a new Big Bang. To understand this, we have to follow the full life cycle of a universe. It begins with the Big Bang, expands, forms stars and galaxies, and over billions of years develops structure. Eventually, stars burn out, galaxies drift apart, black holes dominate. Over immense timescales, even black holes slowly evaporate through Hawking radiation. What remains is a cold, empty universe filled mostly with extremely low-energy photons, radiation stretched across an ever-expanding space. Now, here is the key insight. Photons have no mass, and because they have no mass, they do not experience time in the same way massive objects do. From a photon's perspective, the idea of time passing becomes meaningless. In the far future, when everything has decayed into radiation, the universe loses the ability to define meaningful scales like size or time. Everything becomes scale-free. And in a scale-free state, something strange happens mathematically. The structure of the distant future can be mapped onto the structure of the very early universe. Penrose argues that the infinite expansion of the universe erases all scales, making the end state conformally equivalent to a Big Bang. In simpler terms, the end of one universe can be mathematically reshaped into the beginning of the next. There is no need for a violent bounce or collision, no singular starting point, just a smooth transition where the end becomes the beginning. This creates a picture of the universe as a continuous chain of aeons, each one following the previous without interruption, a cosmos without a true beginning or end. If this idea is correct, it has testable consequences. Penrose predicted that remnants of the previous universe could appear in the cosmic microwave background as faint circular patterns, sometimes called Hawking points. These would be the traces of energy released by evaporating black holes from a prior aeon. Some analyses have claimed hints of such patterns. Others argue they are statistical noise. The debate is still open. But the important point is this. The data we collect from the earliest light in the universe might contain information from before our universe existed. And that brings us to an even more unsettling possibility. What if our universe is just one of many, embedded in a far larger structure? Beyond cyclic models lies an even broader framework, the multiverse. In this view, our universe is not unique, but one of an enormous number of possible universes, each with different physical laws. This idea comes naturally from modern inflationary cosmology and string theory. According to these frameworks, space itself may be constantly expanding in a way that creates bubble universes. Each bubble forms its own universe with its own physical constants, particles, and even different numbers of dimensions. The number of possible configurations in a string theory alone is estimated to be around 10,500. That is not just large, it is beyond human intuition. It means the space of possible universes is unimaginably vast. In this multiverse picture, inflation never fully stops. While it ends in some regions allowing universes like ours to form, it continues elsewhere, endlessly generating new universes. A cosmic foam of expanding bubbles, each one isolated from the others. So what came before our Big Bang in this scenario? Other universes, countless ones. Some that expanded and collapsed almost instantly, others that never formed structure at all. Universes where stars could not exist, universes where chemistry was impossible, universes where the laws of physics prevented complexity from ever emerging. Most of these universes would be lifeless in a deeper sense, not just without life, but without the conditions needed for anything meaningful to form. Our universe appears special because its constants allow structure to develop. Gravity is just strong enough. The cosmological constant is just small enough. Electrons have just the right mass. Change any of these slightly, and the universe becomes uninhabitable. This leads to a controversial idea: selection. We observe a universe capable of supporting life because only such universes can produce observers. In this picture, there is no design required, no intention, just a vast landscape of possibilities, with existence sampling every option. We happen to exist in one of the rare regions where conditions align correctly. And if this is true, then the process that produced our universe is still ongoing. New universes are constantly being created in regions beyond our observable horizon. This means, before the Big Bang is not a single moment. It is an ongoing process that stretches beyond our universe, possibly without beginning or end. But even this may not capture the full picture because our universe still contains subtle hints that something deeper is going on. When cosmologists study the cosmic microwave background, they are essentially looking at the earliest light in the universe. It is a snapshot of the cosmos when it was only about 380,000 years old. This radiation is incredibly uniform, but not perfectly so. Tiny fluctuations in temperature reveal the seeds of galaxies and cosmic structure. These fluctuations have been mapped with extreme precision by missions like Planck. Yet within this data, scientists have found unexpected irregularities patterns that do not fully match theoretical predictions. One of these is the so-called low power at large scales, where the largest structures in the sky show less variation than expected. Another is a hemispherical asymmetry, where one side of the universe appears slightly different from the other. There is also a cold spot that is larger and deeper than statistical models would naturally produce. Individually, these anomalies might be dismissed as random noise, but together they form a pattern that challenges the assumption that the early universe was perfectly uniform. Some researchers suggest these features could be remnants from a pre-inflationary state, something that existed before the rapid expansion smoothed everything out. Inflation is often described as a cosmic reset button. It expands space so rapidly that it erases most traces of what came before. But if inflation was not long or strong enough, then faint signatures of a previous phase could still survive. And if that is true, then we are not just observing the aftermath of the Big Bang, we may be seeing echoes of something earlier. One of the most debated features is a large-scale alignment in the cosmic microwave background, sometimes called the axis of evil. It refers to an unexpected alignment between the largest temperature fluctuations and the geometry of our solar system. In a truly random isotropic universe, such alignments should be extremely unlikely. Yet they appear in multiple datasets, including those from different space missions. While the statistical significance is debated, the fact remains: the universe is not behaving exactly as the simplest models predict. These anomalies do not prove the existence of a pre-Big Bang universe, but they keep the possibility alive. They suggest that our current models may be incomplete, especially when describing the earliest moments of existence. And as scientists continue to refine measurements, the question becomes sharper. Are we seeing random imperfections, or are we seeing physical traces of something that existed before our universe began? That question leads us into the deepest and most uncomfortable territory of modern cosmology. If we step back from all these theories, one pattern becomes clear. Every time we push closer to the beginning of the universe, the idea of a beginning itself becomes less stable. In some models, the universe cycles endlessly. In others, it transitions smoothly between aeons. In others still, it is one bubble among many in a vast multiverse. And in all of them, the Big Bang is no longer a clean starting point. It is a transformation, a boundary, or a phase change. What connects these ideas is not certainty, but evidence that the earliest moments of reality are not fully explained by our current physics. And that is where the anomalies matter most. The cosmic microwave background, the large-scale structure of the universe, and the subtle irregularities we observe all act as clues. Not answers, but clues pointing towards something deeper. If even one of these models is correct, then our universe did not begin in isolation. It emerged from something larger, older, and more complex than anything we currently observe. That raises a profound implication. The concept of nothing before the Big Bang may be a simplification, not a fact. Instead, reality may be continuous across boundaries we once thought were absolute. The beginning of our universe may simply be the transition point from another state of existence that we are only beginning to understand. And yet, despite all of this, there is still no final answer. Every theory has gaps, every model has unresolved questions, The data is suggestive but not decisive. But the direction of modern cosmology is clear. The question of what came before the Big Bang is no longer dismissed. It is one of the most active and serious areas of research in theoretical physics. We are now in a position where the earliest light in the universe might contain information about something that existed before our universe itself. And if that is true, then we are not looking at a beginning at all. We are looking at a continuation. The universe may not have started once. It may have always been in motion, always transforming, always passing through states that appear to us as beginnings. And that changes everything. If you want to explore more deep cosmology, hidden anomalies of the universe, and the latest theories shaping our understanding of reality, make sure to subscribe because the next discovery might completely change what we think existence actually is.